Example 7.5. Object A of mass 0.07 kg moves with simple harmonic motion when it oscillates at a spring. Object B of mass 0.05 kg moves with SHM when it oscillates at a simple pendulum. If the string in the simple pendulum has a length of 0.3, compute the spring constant if both system has the same period of oscillation. So there are two conditions here. One with one condition is about spring, the oscillation of spring. Okay, the mass is attached to the spring and then it oscillates with simple harmonic motion. And then another one, the object with the same mass, okay, move at a simple pendulum. Okay, there are two situations here. Okay, the first situation, okay, for example here, this is the first situation. The mass is attached to the spring and it oscillates back and forth, okay, back and forth with okay, with simple harmonic motion. Okay, and then another one is this is the, okay, for example, this is the object, okay, the same object, the same mass, object with the same mass. So here it will move, okay, again back and forth. The motion is repeated, so we say that the object move with simple harmonic motion. So here, okay, the period of oscillation, so the period of oscillation for situation A, this is A, this is B. So the period of oscillation of A and B are same. Okay. The question asks, compute the spring constant. Okay, K. What is K? Okay. For the first equation, remember omega is equal to sert K over M. This is the equation. Okay, so omega is also equal to 2 pi over T. This is omega is equal to sert K over M. So T, okay, when you rearrange the equation, okay, T is equal to 2 pi sert M over K. Okay, so this is number one from object A. Okay, this is from object A. So object B, okay, I write it here. Remember, omega is equal to sert G over L. Okay, so here again omega is equal to 2 pi over T is equal to sert G over L. So when you rearrange the equation, T is equal to 2 pi, okay, L over G. Okay, look at this one. This is T, this is T. T are same. So therefore, okay, 2 pi M over K is equal to 2 pi sert L over G. Okay, 2 pi can be cancelled. And then sert, okay, so the equation becomes M over K is equal to L over G. So you are asked to find K. So K is equal to mg over L. Okay, so you can calculate here. Okay, this is how you're going to use the equation of omega sert K over M and omega is equal to sert G over L. This is for simple pendulum, and this is for spring system. Hope you clear about this one. Don't confuse. Okay, example 7.6. 7.6. An oscillator is made up of a block of mass 0.5 kg and attached to the spring. Okay, when the oscillator undergoes simple harmonic motion with amplitude 35 cm, it is found to repeat its motion every 0.5 second. Compute the period and angular frequency. Okay, look at this part. It is found to repeat its motion every 0.5. The motion is repeated. That means one complete vibration, okay, or one complete oscillation is equal to the time taken for one complete oscillation or one complete vibration is equal to t. Okay, look at this word, repeat its motion. That means that is the value of t. The motion is repeated every 0.5. So that means that is 0.5 is the period of oscillation. Okay. And then if you want to find the angular frequency is equal to omega is equal to 2 pi over t. So here is 2 pi over 0.5. So we will get here 12.57 radian per second. Okay. And then the spring constant, B, the spring constant. If you know the angular frequency, okay, you can calculate the spring constant. Okay, angular frequency is equal to K over M. So here, you want to find the spring constant. So omega square and then M. Okay, so from here when you calculate, you will get K is equal to 79 Newton per meter. Okay, and then the maximum velocity. Remember the equation of the maximum velocity is equal to omega A. Okay, so the amplitude here, omega, okay, you can get from here omega 12.57, and then A is this one, 35. So A here is 0.35 meter. So when you calculate, you will get 4 meter per second. Okay, then the maximum force acting on the block. So the maximum force, remember Hooke's law. Okay, Hooke's law, F is equal to kx. Okay. Okay, again I repeat, it is optional if you want to write negative or positive sign. Okay, the negative means the displacement is always opposite the direction of F. Okay, so now I write in the positive form like this. F is equal to F kx. Okay, so they want the maximum force. Maximum force, that means X we replace with A, the maximum displacement. Okay, so from here you calculate it. K79 times 0.35. So here you can get the maximum force, 27.65 Newton. Okay, and then the potential and kinetic energy at a position of 12.7 cm from the equilibrium position. Okay. Alright, so here, okay, the potential energy is PE is equal to half kx square. I just substitute the value of x, okay, with 79, and then x is 0.127, and then here is square. So when you calculate this one, okay, when you calculate, you will get 0.64 joule. And then what about the kinetic energy? So kinetic energy is equal to half mv square. Okay, what is the value of v? Okay, we find the value of v first. V is equal to, remember this equation, omega, and then Z a square minus x square. So by using this equation, you can find v. So just substitute the value of omega with, what is the value of omega? 12.57. Okay, 12.57, and then set a is 0.35 square minus 0.127 square. Try to find the answer here of v, and then put the equation, and then substitute this value of v inside this equation. You can get the kinetic energy. Okay, and then the total energy of the system. Okay, the total energy, remember, E is equal to half KA square. Okay, I just take the value of K, 79, and then the value of A is 0.35 square. Okay, so try to calculate it. We will get the total energy. Okay.